Okay, welcome to Chapter 10. So Chapter 10 starts on page 303, and up to now, the first 9 chapters have all been about, writing and analyzing algorithms, theoretical algorithms, turning them into honest-to-God, real, honest-to-God code, and then, figuring out if there was, you got them right, measuring things. So this is more about limitations. So there's a theoretical limitation and an algorithmic limitation. Theoretical limitation means since we haven't got it figured out, there's no amount of code that's going to help. And an algorithmic, limitation is, well, I know how it's supposed to work, but we just can't write a program that does that. So those are two separate kind of things that we haven't really done in the first 9 chapters. Okay, so let's talk about. Let's imagine a scenario where if I had, a faster CPU and more cores and more memory and more everything, it's still not going to help. There are problems out there that are just so big and so complex that because I can't even write the program to figure them out, adding more muscle to it isn't going to help, okay? So if I can't write the program, in other words, no algorithm exists, well then it doesn't matter how many CPU cores I have. And now the other one is you come up with just an algorithmic limitation. For example, the classic example is cracking a password. Is there an algorithm to figure out a password? Well, yeah. I mean, you give it hello world and it crunches it into a hash. You compare the hash to see if it matches. Right? We have an algorithm that does that. What we don't have is an algorithm that does it in reverse. Given a hash, then you need to it'll produce what the clear text is. So the only way you can solve a problem like that is the brute force approach, where you take a guess and you see if it worked. And then you take another guess and you see if that worked. And you take another guess and you see if that worked. That is nasty, nasty. On one of those, if you were to say, how long is it going to take to crack this password? Well, it's theoretically possible. You can get it right on the first try. Not bloody likely, but it's possible. Or you go through every single try that exists and it's the very last one. But it's going to take a really, really, really long time because we don't have an algorithm that takes you directly to it. All we have is, I don't know, let's guess and let's find out if that worked. Okay, so that's a very classic example of what we're talking about. So often, these things are either going to have a big O notation of n factorial or 2 to the n. An n factorial problem would be like the password problem. So if I had a 4-character password versus a 5-character password, it's actually going to be, n factorial. In other words, when you add more length to the password, the amount of possibilities goes up a lot, an awful lot. Okay, so there's a name for this thing. A brute force encryption, where you just guess to see if it's correct, that's considered an algorithmic limit, which means I just don't have an algorithm that can get me directly, so I have no choice but to just try something and see if it works. There's a really cool name for that, and it's being used throughout the rest of this chapter. It's called non-deterministic polynomial time. I know, and it's always abbreviated NP for non-deterministic polynomial time. What that really means is I really can't predict because I don't have enough information. Let me give you a better example of an NP problem. Let's just say that, I don't know, you have a lawn care system, and you're walking down the street with your lawnmower, and somebody comes out and says, "Say, how long is it going to take to mow my grass?" And you'd say, "Well, I don't know. How big is your yard?" See, you can't answer the question because you don't have enough information. If they had provided you the algorithm, well, okay, it's so many acres, then you could say, "Oh, hang on a second. It's going to take me this amount of time. It's cost you that amount of money." But since you don't have that information, okay, then it's non-deterministic, which means I have no idea how long it's going to take to mow your grass. You're going to have to give me some information so I can use my algorithm to figure it out. Okay, so that's an extraordinarily simple and oversimplification, but it's an excellent way of thinking about this thing. So non-deterministic typically means, if you were to kind of break it down into common sense, what it really means is I can't predict. So, I don't have enough information. I can't predict it. Mostly because you're missing some information. Like, tell me how big your yard is. Well, I don't know. Well, then if you don't know, then I can't tell you. All right. On page 305, they start talking about this thing called a Turing machine. Alan Turing, super mathematician, the Enigma project in World War II, blah, blah, blah. You may even seen the movie. Anyway, this is one of those abstract machines that maybe way back when somebody actually built one of these things physically, but it's certainly not the case now. These things are just abstract things. This is a thing to help you think, okay? It's not really an honest-to-God computer that you can buy or run. It's just a thinking exercise. Okay. So, on page 305, a Turing machine is a type of automaton with the following things. It has the current state that we're in, a transition state that it can go through, and then accepting states. So basically it has these three states we're talking about. It's often viewed as a tape where, like a magnetic tape with a read-write head, and it can go forward, backwards. It can read something and then turn right around and write to that tape. So, right, it just goes back and forth, and can read and write to the tape. The tape has a definite left starting point, the start of the data. But the other end of the tape is infinite. In other words, this thing could go on forever, right? So fixed on one end, but not on the other. The read-write head, of course, I mentioned, can move backwards and forwards, and it can change the value of a tape. I can read a 4, and then go, I'm going to change that to a 7, and just go back and forth. Cool. So there's a figure here that kind of sort of shows what they mean. So the diamond is one of the start and stop kind of a feature. So this is a tape representing the data A, B, C, and then you're at state 3 and D, E, F. In other words, your pointer, so to speak, is at 3. And so you have something to the left, you have the current thing, and you have something to the right. Okay. Now, the utility of this is somewhat difficult to grasp up front. But trust me, when we get a little bit further into this thinking exercise, this thought exercise is going to make a little bit more sense. Okay, so they have a combination of states, symbols, and then transition. And transition is typically just a movement of left to right, right? I transition from 3 to 2, which means my pointer goes from D to C. Okay, that's all that really means in this particular case. Okay, all right. So before we get into this, let's review all the rest of the automatons because we had a bunch of them. All right, so this new one, this is often abbreviated TM for Turing machine. Okay, so first one, remember we have a finite automaton. Okay, remember that from the previous chapter. And we use that for regular languages. Okay, that's a good use case for it. Then we had a push-down automaton, and it was designed for like context-free languages where you could have some, something inside something. You have nested things. Remember all that? And then the Turing machine is one where it can do recursive things where it can have a loop, go over things over and over again, and one called recursive enumerable. And let's just go ahead and go talk about what those terms mean. Recursive means that the Turing machine will halt when it gets to the end. In other words, you're asking it a question like, does this equal that? And so it goes, ding, and it comes up and says yes, or it says no. So all the inputs either end up with a yes or a no symbol, okay? You could say, for example, if you asked it, is this symbol in the language? Remember back in the day when we were doing that kind of thing. You just rip through it and go, no, that symbol's not in the language. I checked all the language and it ain't there. Okay, there's other things you can do, but that's just a simple one. Recursive enumerable means that the Turing machine could just go into an infinite loop, okay, where it won't actually halt at all, okay? So those are two different techniques or use cases where a Turing machine would work. So at least one thing, one word in the language would cause this guy to go into a loop. So when looking for all words, let's say I want a list of all words in a language, okay? Well, that'd be kind of easy with the recursive because you could just spit them all out. But with a recursive enumerable, you need to fix it to run words in parallel. Because if one of them stalls, you don't want to just have the rest of them stall. In other words, the only way you could do it with a recursive enumerable is if you had like, I don't know, half a dozen of these Turing machines. And so if one of them killed off, the others would just keep on going. Okay? So that's not a very good way of doing things. Okay. On 310, they start talking about function calculators. And yes, if you had a function that, I don't know, something simple like adding two numbers together or whatever, then yes, Turing machine can use to add numbers together or do multiplication or whatever you want it to do. So it says Turing machines can also be used to calculate the value of a function. Finite and pushdowns really can't because they only output the final state, whatever that thing is. So a Turing machine can perform calculations. Cool. And so we can combine multiple Turing machines together to get compound functions. Like, how like when you're calculating interest, right? Where you have like a compound formula. Well, I could use two TMs, or 3 or 4, and write this thing so that I can do compound interest, right? Okay, cool. So on page 311, they start talk about designing a Turing machine. Now, I am not going to ask you to design a Turing machine or write code for a Turing machine. That's not something we're going to do in this chapter. This whole concept is designed to sharpen your brain, okay? This is exercise, okay? Like doing push-ups. There's no value in doing a push-up directly, but it does help you do your job of warehouse worker because you can lift boxes easier, right? But the push-ups themselves you're not getting paid for that. Well, just like that, the Turing machine is to sharpen your mind. It's not actually something you're going to do for a living, but it'll make your mind sharper so that you could go do other things better. Okay. So conditional statements, we're talking about if, case, those kind of things. Where you choose an action based upon a condition. Well, that's perfect for how the transition states work. The current state and the current symbol determine what the next one is. So each state can have a task associated with it. All right. So loops, like a while, do, those kind of things, at state changes can have multiple tasks for it to do. And this is actually pretty good for tasks. You can combine things until they fail, like moving the read-write head until you find an A, right? Move the read-write head to the left until you find an A. Nope, didn't find it, found it, that kind of stuff, okay? So that's kind of like a loop, just keep going, stop, all right? That's like a while loop. It sounds like a while loop. Okay, so there's a goofy example on page 312. Now, I'm going to try to read the description of this thing in 312, okay? And again, try to follow along because this is a little mind-numbing, I confess. So they talk about, finding A and then changing it to an X. Remember, I can find the letter A and then boop, change it to an X. And then scan to the right for B. And if you find that, change it to a Y. And then scan to the right for a C. And if you change that, change it to a Z. And then rewind, boop, and try again. Right? So find another A, another B, another C. Okay? So you're going, finding something, changing it, finding something, changes it, finding something, changes, then whoop, do it again, and again, and again. Rewind and repeat until there's no more choices to be found. In other words, all the A's have been changed, and all the B's have been changed, all the C's have been changed. Sounds kind of simple, doesn't it? Okay, we're coming up on the 15-minute mark, so you guys know how this works.